call your attention to where I want to start today, I want to do a brief reminder. And that reminder starts with net force equals MA. This is dynamics. This is when we no longer have a net force of zero. We have a circumstance in which the forces are unbalanced, and we know that when the forces are unbalanced, the effectiveness of a force, meaning how capable is that force of causing an acceleration, is tempered by the object itself. The more inertia the object has, the less effective a force is at moving it. I use that phrasing all the time because I want to remind you, inertia is about resistance to changes in motion, resistance to acceleration. So a force is going to be less effective on an object with more inertia. Why? Because an object with more inertia is harder to move. I said this at the very beginning of the year, and a lot of you didn't fully appreciate it, but inertia is the key to this class. If you understand inertia, you will understand most of the tenets of this class. Momentum is all about inertia, and Newton's second law is all about inertia. Although we tend to think of this part as being the complicated part, this is just how things are pushing on the object. The truth is, how the object behaves is 100% tied up here. But first semester, we took a simplistic look at this. We just assumed that all the forces act at the center of an object. And that's not true. The forces act at the point of application of the force, which is why we must understand the concept of torque. Torque has a similar concept to Newton's second law, which states that if you attempt to try and twist or turn an object, the effectiveness of those torques will be dependent on the inertia of the object. However, you guys tend to see this in simplistic terms. So let's consider our lab where you applied a torque by taping a string onto the side of the object and pulling on the string. Right? How you were able to spin the object depended on how hard you pulled on the string. You never changed the inertia of the object, you changed how hard you pulled on the string. And when you pulled harder on the string, the object responded by accelerating faster. Is that a reasonable discussion of what you did? Torque plays out in other places that you may not be thinking about. Let's say you have a box you want to push across the floor, and you're going to apply a force to the box. You are all aware that there's probably a variety of forces acting on the box. So if you're here and you're going to push on the box, those forces are going to look something like maybe your pushing force acting on the box, the weight of the box, the normal force acting on the box, and probably friction acting on the box. Does that seem reasonable as the forces that act on the box? But the truth is, this is not necessarily where those forces act. If we consider where those forces actually act, there's going to be you pushing on the box, which probably acts something like here. Right? Something where your arms are if you're going to push directly on the box in front of you. There's going to be friction acting on the box. Well, that's going to act down here along the bottom surface of the box. There's going to be gravity acting on the box, and that's going to act assuming that the center of mass of the box is at its center. Will act, say, here. And then there's the normal force on the box, which will act on the surface as well. But it acts at the surface. These forces all act in different places on the object. And if you look closely, there's a probability that although the forces could balance out and the box could slide to the right, it is possible the torques won't balance out. If you look carefully at this, I think the friction and the pushing force could cause the box to rotate because they're being applied in a location that is clearly away from a possible axis of rotation. And you know this, and any time that you... So when we talk about how forces are applied and their effectiveness, we now have to take into account where those forces are applied. Now, whether this thing will tip over or not depends on a number of factors, and one of those will be the inertia of the object. So you may be able to apply these forces and nothing happens. It slides across the room as you would anticipate. But you've also probably been in a circumstance where it was sliding along just fine until you came across that one pebble that was on the ground. You hit that pebble, suddenly another force sprung to life, pushing away from the axis of rotation and pushed the thing right over. I am confident something like this has happened to one or two of you in the room. And the idea is that torque depends on where the forces are applied and depends on the effectiveness, the inertia of the object. Today I want to talk about inertia and then use that in problems to deal with how effective a torque can be at causing an object to rotate. Imagine a few things from your life. So here's what I want to use as an example. I want you to imagine I'm going to take a meter stick and I'm going to rotate it about one end. So I'm going to spin it about an end. If we consider for just this activity that centimeter 49, which is sitting right there, the only way it accelerates this way is if there is a force acting on it. So there must be a force on centimeter 49, which causes the piece of mass, number 49, that piece also accelerates. So there's the acceleration of piece number 49. All right? Are we following along okay? Now, something causes that force. But the thing I want to kind of emphasize is that there's also a piece over here, say piece number 89. And piece number 89 experiences a force. And then there's the mass of piece number 89 and the acceleration of piece number 89. Right, it's a meter stick, so I'm just picking random pieces. Now, the mass of each of these pieces is probably the same because each one of them is 1 centimeter, right? So if we assume a meter stick has uniform mass, each piece of these is going to be the same mass. But the acceleration of piece number 89 is different than the acceleration of piece number 49. We know that because it's all one thing and it's rotating. And we already talked about kinematics, and we know from kinematics that the linear acceleration is related to the angular acceleration times the radius. Right? That was what we talked about earlier. So I could take each of these and recognize that they all have different accelerations. But it also suggests that the force on piece number 89 is greater than the force on piece number 49 because they have different accelerations, same mass, so that force on that piece over there is going to be greater. And if you've ever watched a group of kids all holding hands trying to go in a circle, that's why the last kids all the way out there are all lagging behind. They have to go faster and you have to pull them harder because they're traveling in a bigger circle. So this is the same kind of thing. Now, this part might be hard for you to understand, but I still want to move forward with it. Let's take a look at piece number 49 for a minute again. Piece number 49 has mass m. I'm going to assume that all the pieces have the same mass. I think that's not unreasonable. But actually, for this argument, let's just leave them numbered. So I'll say 49. Just in case we have something where the object gets heavier as you go to one end or something like that, that would allow this to be more flexible. But I'm going to replace something here. The whole object will experience the same acceleration, angular acceleration. So I'm going to change each of the linear accelerations into their angular acceleration counterpart, which means this is going to be alpha times r49, right? Because r49 is 49 centimeters from the axis of rotation. And piece number 89 will have mass 89, but it's going to have an acceleration times r89, because it's 89 centimeters from the axis of rotation. Now, this part's going to be maybe tough to understand, so help me out or pay attention, whatever you want. If I want the whole thing to rotate, I could have just applied a force somewhere on the middle of the meter stick. And that force would cause a torque. Because we know how torque works now. We know the definition of a torque is R times F times sine of the angle. And this equals torque. So if I want to consider the torque on piece 49. Well, the torque on piece 49 would be R49 times F49. This is the amount of torque applied. And I'm going to assume the angle's 90 degrees, and I think that's a reasonable thing to assume. Everybody okay so far following this? Well, here's the thing. I said I'd bring a first principle in. Here's a first principle. Net torque equals I alpha. Each piece of this meter stick gets a small amount of torque, but the total torque required for the meter stick to rotate would be the sum of all those individual torques. If this represents all the individual forces acting on each individual mass, then I could sum up all the torques, and that would give me the total torque necessary to rotate the meter stick. So I'm going to consider net torque being the sum of the torque on centimeter 1 all the way to the torque on centimeter 49, the torque on centimeter 89, all the way to the end. I'm going to add up all of those torques. That okay so far? Does that make reasonable sense to you? All right. I'm going to move the picture out of the way so we can just focus on this. I'm going to do some substitution. And I'm not going to substitute everything. I'm going to substitute a couple of placeholders in. For example, I'm noticing a pattern here. So torque 49 just by itself is R49 times F49, but F49 is M49 times alpha times R49. All right, do you see all of that? But there's 100 of them. I'm not going to write all 100 of them. Is that okay? Now, a little bit of algebra. Oh, you got to be kidding. Would show you this, correct? Now, does it take much to realize that there's an alpha in all of these? So I could write this as like that. So this is the last piece I want you to write down. If I were to use the summation symbol to write up all of these different pieces of mass, I would say it's the sum of every piece of mass of the meter stick times where each piece is squared, starting with piece number 1 and ending with the last piece of the meter stick. This is where moment of inertia comes from. All right.